Hello, my name is Jan Van Sickle, and I'd like to welcome you to the GPS course. First slide here is Block 2 satellite of the majority, really, of the current constellation of GPS satellites. In this first lesson, we will be talking about the GPS signal. I think it's a good place to begin because it gives you a general idea of how GPS functions, how positions are derived from the system. This capability, of course, is at the heart of the application of GPS to various components. GPS is often compared to triangulation, which is actually not entirely correct. More correct would be trilateration. Trilateration is based upon distances rather than the intersection of lines based on angles. Now, in a terrestrial survey, as indicated in this image here, there would probably be a minimum of 3 control stations and then intersecting distances. Here I think L1, L2, and L3. Now, this is very similar, actually, to what's done with GPS, except instead of the control points being on the surface of the Earth, they are, in fact, orbiting. They are the satellites themselves. Those are the control points orbiting 20,000 kilometers above the Earth. And there's another difference. Instead of there being 3 lines intersecting at the unknown point, there are actually 4. The reason there need to be a minimum of 4 is that there are 4 unknowns, x, y, z, and time. Those needed to be solved, and therefore there need to be a minimum of 4 measurements with GPS. But there are some similarities between this image of terrestrial surveying and the GPS procedure. One thing is that the distances need to be paired with their correct control point. Another is that the distances measured electronically are based upon the speed of light, the speed of electromagnetic radiation, and the amount of time that the signal takes to go from the control point to the unknown point and back in some cases, although GPS is one way. We'll talk more about that. There's other similarities too, but these ideas of distances being used, several simultaneous distances being used to an unknown point, is probably one of the fundamental ideas behind the functioning of GPS. I mentioned time as being one of the unknowns, and in fact it is. And its measurement is essential, as it says here, to GPS surveying in many ways. Obviously, of course, the elapsed time of the electromagnetic signal. But there are several clocks, or oscillators, perhaps is the more correct term, associated with the systems in GPS. There are clocks, or oscillators, in the satellites and in the receivers as well. Now, control, both GPS and trilateration surveys on the terrestrial side, have to have control points. And as I mentioned, in this case, it's the satellites themselves. This is a point we'll return to more than once. So, of course, obviously, it's important to know where the satellite is in the sky at the moment that a measurement is taken. This is the office of the ephemeris of the satellite. Now, GPS is a passive system. That means that the receivers don't send any signal whatsoever to the satellites. The satellites broadcast and the receivers receive. In some ways similar to what a car radio does. It receives but doesn't send. So that's the sense in which it is passive. Therefore, if we are to measure distances from the satellite to the receiver, and that is the foundation of GPS surveying, there's some information that needs to be communicated from the satellite to the receiver. And therefore, it needs to come down, so to speak, on the signal from the satellite to the receiver.
One aspect is the time on the satellite, because of course the elapsed time that the signal spends going from one place to the other is the basis of the distance measurement. And time is important in other ways, but clearly that is important, to know the time on the satellite, the instant that the signal left. Secondly, the position of the moving satellite is critical, and that's because, just as on a terrestrial survey, the coordinate, if you will, of the satellite at that moment is important so that it can be used to derive the position of the receiver. Now, in a terrestrial survey, instantaneous position hardly comes into it because, of course, the instrument is stationary on the Earth's surface. But with the satellites moving at a pretty tremendous rate of speed, the ephemeris, as I mentioned, needs to be the coordinate, so to speak, at an instant of time. This is another way, of course, that time is important. And then, some information about the atmosphere. Well, if you're familiar with EDM surveying, electronic distance measuring surveying, you know that when an electromagnetic signal goes through atmosphere, it can be attenuated by the humidity, the temperature, the barometric pressure in the troposphere. And so this is introduced into the processing of the distances that are shot with EDM instruments. Now, in the case of GPS, of course, this signal is going through a good deal more of the atmosphere than even the longest EDM shot. The first component of the atmosphere that it encounters is the ionosphere, which has some different characteristics than the troposphere. And then after that, of course, it goes through the troposphere, but it goes through a good deal of atmosphere. And therefore, the signal can be attenuated rather dramatically. And this is important to have some concept of the atmosphere through which the signal is passing so that these delays, if you will, can be introduced into the answer, into the solution. And then some sort of satellite identification system is required. This is because each distance that a receiver has must be correlated to the control point or the satellite from which it came. And since it will be observing a minimum of 4, and most cases probably more, satellites, it needs to be able to put the appropriate range, the appropriate distance or length, to the correct satellite. So it needs to identify each one of those signals. This is just some of the information that needs to come down on that signal from the satellite to the receiver. It's quite a list, and is actually even a little bit longer than this. The question is, how does this information make its way from the satellite to the receiver? And the answer is the navigation message. Now, this slide shows the 5 subframes of the current navigation message. There is some modernization in the works for this signal, but it is this currently, as you see. Now, each word, TLM, for example, stands for telemetry, and HOW stands for handover word. I'll say a little bit about those, but the more important aspect at the moment is over on the right-hand side, the subframe, clock correction, GPS, weak satellite health, etc. in subframe 1, and then 2 and 3 are devoted to the ephemeris, and then 4 and 5, as you see, ionosphere, which we've talked about a bit, and then of course PRN satellite almanac is mentioned here as well. This goes to the identification system that I mentioned. Now there's a blurb here about the navigation message. There are 10 30-bit words, 6 seconds. The entire navigation message contains 37,500 bits and so on. Perhaps it is important to take a look that 12.5 minutes to broadcast and receive at 50 bits per second is the amount of time that it takes to acquire the entire navigation message from a cold boot with a GPS receiver. In other words, it's not instantaneous. It does take a bit of time for the receiver to update its navigation message. This is an important piece of information we'll be talking about a little bit later. But the essential point here is that this message is the fundamental basis for the satellite to communicate instantaneously with the receiver. Instantaneously in the sense that it is capable of telling the receiver where the satellite is after the receiver has acquired the signal from the satellite. It comes in at a pretty low frequency, 50 hertz, and it does take some time for the satellite to acquire the whole thing. But it does have the essential information. Now, the clock correction, which we'll talk a bit about, is one of the ways that the satellite can tell the receiver what time it is on board the satellite. The ephemeris, as I mentioned, is the coordinate system. It tells the receiver where the satellite is at an instant of time. The ionosphere is that atmospheric information that will allow the receiver to make some corrections on the length that it receives from a particular satellite. Then the PRN is actually pseudo-random noise. That's what PRN stands for. One of the reasons that that's there is the term is communicating that the signals that the receiver uses for positioning appear to be random noise. But in fact it's pseudo, the false random noise, because they are very well designed. They are just seem to be irregular. And the PRN numbers 25 to 32 mean that satellites from number 25 to number 32 can have their almanac, in other words, just a little slice of their ephemeris, in subframe number 4. Now the PRNs from 1 to 24, those satellites have their almanac, in other words, a little bit of their ephemeris, in subframe number 5. Now you might wonder why they are there. This is that identification system. In other words, when a receiver acquires the navigation message from one satellite, embedded in that navigation message there's a bit of information, just a bit, that will tell the receiver where it can find the rest of the constellation in the sky. This helps it acquire the additional satellites after it's got the first one. That's what the satellite almanac does. Well, the question might arise in your mind, where does this navigation message come from and the information embedded therein? It comes from what is known as the control segment. There are 3 segments in the GPS system: the user segment, the control segment, and the space segment. The space segment is obviously the satellites themselves. The user segment are all of us with our GPS receivers, and the control segment, well, here's a slide that shows you the expanded control segment that is currently operational. It's a good thing that we have the control segment a little bit modernized from what it once was. We'll talk more about that in the future, but here we have the stations, some of them monitor stations, and then some of them actually have upload capability as well. In general, what happens is this. The GPS satellites are tracked by at least now 2 of these stations simultaneously all the time. Now, by tracking them, they are able to do several things. For example, since these stations are at known positions on the surface of the Earth, they are able to collect the signals from the satellites and know how much they have been delayed or attenuated by the atmosphere, for example. They are also able to track them and determine their path in their orbit. From this, they can calculate the ephemeris. Also, they are able to compare the signal coming from the satellite with their atomic clock that is right there at the monitoring station. See the difference between the two, and then upload to the satellite a clock correction. Well, this is how they derive the information, at least, but in terms of the upload, All of the information from the tracking stations goes to that master control station in Colorado Springs at Schriever Air Force Base, where calculations are done in terms of all of these components that we've just seen are in the navigation message. Then those corrections go back to the upload stations and are uploaded back to the satellites. That's where the information that is in the navigation message comes from. It's the control stations in the control segment on the surface of the Earth comparing the received signal from the satellite with their satellite clock, with their atomic clock, and with their actual known position. This way, they can derive the corrections that go into the satellite's navigation message. When the receiver, the GPS receiver, collects that navigation message, it's able to do some of the corrections it needs to be able to derive a correct position on the surface of the Earth. Since we've talked some about time, it probably is a good moment to discuss the time standard that is used with GPS. Now, worldwide, the Coordinated Universal Time, or UTC, standard is well known and is driven by several atomic clocks around the surface of the Earth. However, Coordinated Universal Time, as derived from these clocks, is in some sense more accurate than the actual rotation of the planet itself. They sort of get out of sync with each other. So therefore, to keep UTC connected to the planet, periodically leap seconds are added to Coordinated Universal Time. Now, since GPS is space-based, since the satellites are orbiting the Earth, the decision was made that GPS time would have the same rate as UTC, but it would not use leap seconds. So, on January 6th, 1980, it was decided that GPS time and UTC would be exactly together. They would be the same. But since then, there have been leap seconds added, and currently GPS time is exactly 14 seconds ahead of UTC, Coordinated Universal Time. That is complicating the relationship, I guess, a little bit, but perhaps the most important thing to remember is that the rate of GPS time is the same as the rate of UTC. Now, the control segment keeps track of that, as I tried to describe the previous slide. And by making this comparison between the two, it uploads this clock correction to the satellites. It's available to your receiver in the navigation message. They try to keep the rate of GPS time at the satellite within 1 microsecond of the rate of UTC. Now, of course, the oscillators or clocks in the satellites have a tendency to drift. They're not perfect timekeepers, and they're affected by several things, moving in and out of the shadow of the Earth, gravitational changes, and so on, cause the clocks to not oscillate perfectly. Now, the control segment keeps the rate within 1 microsecond and usually within 25 nanoseconds. What I mean by that is that they don't constantly tweak the clocks or the oscillators in the satellites to keep them perfectly on GPS time. They let them wander a little bit within the limit of 1 microsecond. They find that by doing this, it keeps the clocks or the oscillators in the satellites healthy longer. It extends their life. And one of the things you'll note is that one of the first things to go to stop working properly on a satellite are the clocks. And that's why most of them have at least two, a cesium and rubidium oscillators. So the message is that the control segment introduces a clock correction into the navigation message that gives your receiver a way to correlate the drift of the oscillator in the satellite with GPS time. This is one way to keep the time standard within limits. Other time-sensitive information, of course, includes the ephemeris, this coordinate, if we will, of the satellite in space. Now the control segment also uploads the ephemerides to the navigation message for each individual satellite. Now it's done in Keplerian components, but in fact the satellites are close enough to the Earth that their ephemerides change with time. Its orbit of a GPS satellite is affected by lots of biases, and therefore the ephemeris needs to be updated constantly to keep it within reason, within accuracy required to get good positions on the Earth's surface. Because, of course, these are the control points. These are the points from which the distances must be derived. So one of the pieces of information that is in the ephemeris subframes is called the IODE, or the issue of data ephemeris. Sort of puts a time stamp on the ephemeris that the receiver gets from the navigation message. And in subframe 4 as well, there is the atmospheric correction that has been uploaded to the satellite from the control segment. As the slide here indicates, the signal of the GPS satellite going through the ionosphere can be slowed, delayed. Now here it's indicated as a change in angle, which is probably not entirely correct. It's that the signal appears to slow down. Now the reason that the control segment can quantify this is because, as I said, the tracking station is at a known point. But one of the critical things that is important to understand about the GPS signal as it goes through the ionosphere is that it is dispersive, meaning that the two frequencies, and GPS satellites do broadcast two frequencies, which are known as L1 and L2. These two frequencies are affected differently. Their propagation rates, they're slowed differently in the ionosphere. They're not slowed in exactly the same rate. We'll talk more about that in a little bit. But for the moment, it's sufficient to say that a single frequency receiver, and there are such things, of course, a single frequency GPS receiver is somewhat handicapped by the fact that it cannot model, if you will, the ionosphere. If it only has one frequency, it can't take advantage of the fact that if it can collect two frequencies, both frequencies, L1 and L2 from a GPS satellite, it can quantify for itself, actually, how much the signals have been affected by the ionosphere. In the case of a single frequency GPS receiver, it must rely almost completely on the navigation message atmospheric correction. The reason this is a bit of a handicap is that, for example, the atmosphere above Kwajalein in the Pacific might be quite different than the atmosphere above your GPS receiver in the continental U.S. And that's part of the reason that the navigation message in general is not as perfect as we perhaps would like it to be. The almanac in subframes 4 and 5 tell the receiver where to find the satellites, and these little pieces, these little truncated ephemerides in the almanac help it do that. Now, the MAD navigation message repeats every 12.5 minutes. The time to download it, or for a receiver to actually acquire the entire navigation message, can take 12.5 up to 25 minutes on a cold boot, meaning starting a receiver that hasn't been turned on for a good length of time and needs to acquire the entire navigation message. But once it does acquire the whole thing, it can then spot the other satellites and acquire them pretty quickly after that. Also, there's information about the satellite health in the navigation message. This is important because, of course, GPS satellites operate in a rather hostile environment, and if they're having trouble, if there's something wrong, in other words, if some of the clocks, there are usually two types, rubidium and cesium, and up to 4 oscillators on the satellites. This health data allows the receiver to give some information about which satellites might not be entirely correct to track. They might receive a signal, a receiver might receive a signal and be able to say that, well, this signal is unhealthy and so shouldn't be used in the positioning. Well, here's the navigation message again, just a little bit of information concerning the TLM or telemetry word and the HOW or handover word. The telemetry word indicates the status of uploading at the control segment, if it's in process or not. This allows your receiver to know that. Also, it allows it to know the beginning of each word from the data string. The handover word is useful in a couple of ways, but probably most importantly to tell your receiver where the satellite is in its broadcast of the codes. There are 2 codes in GPS. We will talk more about those, of course. The CA code, which is the civilian access code, and then the P code, which is the precise code. The P code itself is classified and for use by military only, and the civilian access code is useful to us all. It is available. So these 2 words, there's much more to know about them, but I don't think we want to go into them in great detail at the moment. However, what we do want to talk about in detail are the codes themselves. Now, the navigation message can be thought of as the navigation code, but there are others. The positioning that is, of course, the point of GPS is really the office of the P code and the CA code, the precise code and the civilian access code. Like the navigation message, they carry information down from the satellite to the receiver. They're carried on the carrier waves. L1 and L2 are the standard carrier waves currently. There will be modernization on that with an L5 frequency coming in the future, but currently L1 and L2. Now, the way that these codes are impressed onto the carrier is an important piece of information. For example, when you listen to a radio in your car and the announcer says you're listening to, let's say, 760 megahertz, well, of course, you're not listening to 760 megahertz. If you could hear it, it would be a constant buzz. What you hear is, of course, the modulation of the carrier, and the same thing is true with GPS. But with a radio, of course, the modulation typically is either frequency modulation or amplitude modulation for FM and AM, respectively. But with GPS, the modulation is differently done. It is done with phase modulation, and that's what this image here is intending to indicate. As you see, we're talking here about the P code, and with this image, we have a sine wave with particularly sharp corners, but still a sine wave nonetheless. And you'll notice that up at the top of the blue line, there's a 1 and a 0 and a 1 and a 1 and a 0 and a 0, a binary code. But notice that these code chips, as they're called, transition from 1 to 0 and back to 1. They change, that is, when this line, this blue line, goes up to the center and then back down again or back up again. In other words, it doesn't follow the particular sine wave typical pattern of going up to the top and then down to the bottom, and it stops in the middle. When that happens, there's a transition from the 1 to the 0. Now, on the next piece, let's say we go from a 1 to a 1. It doesn't change. Well, in this case, there is no interruption of the normal sine wave path, and it only occurs a shift from 1 to 0 when, again, it changes at the center line. This is a good illustration of what phase modulation is. Obviously, if the receiver can know the shift from 1 to 0 and 0 to 1, this indicates a code that it can use. Now, the P code, as it says here, is generated at a rate of 10.23 million bits per second. We'll find out that this is the fundamental clock rate. But it's available on L1 and L2. It's a very long code. It repeats every 7 days. The entire code is renewed every 37 weeks. But all GPS satellites broadcast their codes on the 2 frequencies, as I mentioned. But also, a GPS receiver has to be able to distinguish one satellite's transmission from another. This goes back to our original point of the receiver has to be able to correlate the distances that it derives with the satellite from which it came. Now, one method to do this is that this very long 37-week P code is assigned in weekly increments to particular satellites. Like, for example, Space Vehicle 14, or SV-14, is named that because it broadcasts the 14th week of the P code. And the receiver, knowing that, can determine that it's looking at that particular segment of the code, so it must be coming from SV-14. Now, the CA code, or Civilian Acquisition or Access Code, is generated 10 times slower than the P code. Well, this is interesting because actually it is done on purpose. It is done by design, but still it is impressed upon the carrier, again, by phase modulation. Now, here we have the green line, and it's again the sine wave that only transitions when it reaches that center line, goes back up a phase shift, and then the code chip goes from the 1 to the 0. In the fundamental clock rate is 10.23 megahertz, but CA code is generated at 1.023 megabits per second. Now, the CA code is the vehicle for the so-called Standard Positioning Service, which is used for civilian applications. Modernization will introduce a new civilian code called L2C. More about that later. When the codes were designed by the Department of Defense, the concept was that the Standard Positioning Service, as opposed to the Precise Positioning Service, would provide a level of positioning at plus or minus 100 meters 95% of the time. But there was a surprise. It turned out that actually CA code was providing users, civilian users, with much better accuracy in the realm of 20 meters to 40 meters. While this was in some sense good news, it was one of the reasons that so-called selective availability was introduced. This was the dithering, the jiggling, if you will, of the clocks in the satellites so that the oscillators in the satellite to try to disrupt that level of accuracy. For single frequency users, this was at purposeful degradation of the positioning that could be had from GPS. Well, the good news is this was switched off on May 2nd of 2000 by presidential order. Now perhaps is a good time to explain how ranging with electromagnetic signals works. It's convenient to talk about it in terms of an electronic distance measuring device. It's a good place to start in the explanation. Now here it's a two-way system in which the EDM on the left sends out a signal of very constant frequency to a retroprism or a reflector, corner cube, so that the signal goes out, reflects off of the retroprism, and returns to the EDM. This is good because then the EDM can analyze the signal and determine the distance. So it's a very constant frequency, of course, at the speed of light. The idea is to determine the elapsed time of this two-way trip, and by a simple calculation, divide it by 2, and there's the distance between the two stations. You have the distance to derive, which is indicated by rho, the elapsed time, by delta t, and the rate of the electromagnetic radiation, the speed of light, c. Well, unlike the EDM, the GPS cannot take advantage of a two-way system. The signal comes from the GPS satellite and goes down to the receiver. Now, again, it's the same concept, though. The elapsed time, electromagnetic signal of constant frequency, and therefore the elapsed time was the way to determine the distance. But, unfortunately, this would mean that the clock, the oscillator, and the GPS satellite, and the clock and the GPS receiver would have to be perfectly synchronized. That's awfully difficult to do. And on top of that, a discrepancy of 1/1,000,000 of a second actually creates a range error of 300 meters. I like to bring up the fact that 1 nanosecond of speed of light is approximately a foot. So you can see that this sort of perfect synchronization is not in the cards. So we have to solve for time with GPS. But let's go back to the idea of how the distances are measured with an EDM. But before we get into that, a little bit about phase angles. Because as I said, it's the modulation on the carrier by phase that is the method of attaching the codes to the GPS L1 and L2 carriers. Here's a sine wave. 0, 90, 180, 270, and 360 are known as phase angles in a single wavelength. Now the oscillators in the EDM or in the GPS satellite have the ability to create very constant wavelengths because, like clocks or oscillators, they're known as frequency standards. So they can create electromagnetic energy that has a very constant wavelength and therefore phase angles at definite distances. One wavelength might be any sort of distance really, but the phase angles for a full cycle go from 0 to 360 as indicated here. This graphic on the slide shows again the EDM sending out the transmitted wave in blue with the phase angles indicated as before. And then the signal goes off to the retroprism and returns. When it returns, here in the dashed red line, we see the phase angles. But notice that the return signal does not come back exactly in phase with the transmitted wave. Now the key element here is that the EDM generates a wave that is exactly the same as the wave it transmitted and sort of keeps it at home in the circuits of the EDM so that it can compare the reflected wave, the returned wave, with the signal that it has in its own circuits, which is exactly the same as the wave it transmitted. Now, by comparing the return wave, the one here in the dashed red line, with the exact replica of the transmitted wave in the blue, it can determine how much the return wave is phase shifted or out of phase with its original transmitted wave. Now, when it can do that comparison and get that value, the distance between the EDM and the reflector is then indicated by this formula here. Rho equals n, the number of full wavelengths of the modulated carriers completed, plus d, the fractional part at the end, divided by 2. Why divided by 2? Because, of course, in this particular case, the two-way ranging, the signal has traveled the distance twice, going out and coming back. Here is that comparison, the reference wave in blue with the reflected wave with the dashed red line. Now, as in the previous slide, the reflected wave came back out of phase by 1/4 of a wavelength. Now with an EDM, as it says down here at the bottom, we can actually send out wavelengths of varying length. For example, if we sent out a wavelength of 100 meters with an EDM, then by knowing the fractional part of that 100-meter wavelength, it would be possible to determine the tens of meters of the distance. The hundreds of meters of the overall distance could be resolved by sending out a wavelength of 1,000 meters and then doing this phase comparison that you see in this slide. But this is a function of the fact that the EDM survey can send out the wave and have it return from where it came and compare the reference wave with the returned wave. By comparing phase angles, it can determine the fractional part of the wavelength that went out as that component of the distance and build up the distance from thousands to hundreds to feet to decimals of feet by sending out wavelengths of different size. However, with a GPS survey, that's not possible. We only have L1 and L2, constant wavelengths. So therefore, it's possible at the receiver, by this same technique, to determine the fractional part of the wavelength, that component of the distance. But what is unknown is the number of full wavelengths between the receiver and the satellite. That's known as N, or the integer ambiguity. We will be talking some more about that. As it says here, this phase comparison is convenient for the EDM two-way system, but impossible in the ranging of a GPS system. GPS ranging has to use a different strategy to solve this cycle ambiguity or integer ambiguity problem, because the satellite broadcasts on only 2 carriers, and they have constant wavelengths. And as they propagate in one direction from the satellite to the receiver, the integer ambiguity remains. Therefore, unlike an EDM measurement, the wavelengths of these carriers can't be changed to resolve the cycle ambiguity problem, the number of cycles between transmission, and reception. So we'll talk more about how that is done. But this leads to a discussion of the observables in GPS. There are 2 observables that are of interest right at the moment. One is the code that we've talked about that is modulated onto the carrier. That is an observable. These are known as the pseudo-range codes. Well, there's another type of observable too, and that's the carrier itself. Without consideration of the codes, of course, L1 and L2 can be called an observable. Each one can be an observable. And also the codes, the P code and the CA code, those are also observables. Now in the upper part of this slide, you see the pseudo-range codes indicated by square waves. And in the lower part, you see the carrier, which is just a constant sine wave, not modulated, just a constant wave. And both of these are observables. The pseudo-range in many GPS receivers is used as the preliminary step to the final position done by the carrier phase measurement. And this is something that is, I think, important to understand. Most GPS receivers use the pseudo-range code, that indicated by these square waves, as sort of the front door, the way to begin the determination of a position. And then frequently they switch to the carrier to refine that position and become much more accurate than is available from the code phase or the pseudo-range code position.
Here on slide 21, we see the carrier wave modulated by phase, as was discussed earlier, instead of FM or AM. The L1 and L2, of course, are the carriers. This little image up here at the top of the slide, which we'll see in a larger version later, is L1. The method is called binary phase shift key, or BPSK. The only reason I bring that up is later we'll be talking about a different kind of modulation scheme, which is BOC, or binary offset carrier. Now, the binary phase shift key is the technique used in the navigation message, the P code and the CA code. All of them use these zeros and ones. Now, the binary biphase modulation is accomplished by these shifts in phase of 180 degrees. This is the picture I had earlier of how the sine wave goes up to the middle and then goes right back down again. When the value of the message is changed from a 0 to a 1, or from a 1 to a 0, the phase of the carrier is instantly reversed. It's flipped 180 degrees. And each one of these crossings creates a code chip. And the 0 represents the normal state, and the 1 represents the mirror image state. Here on slide 22, we see the full version of this image, L1 carrier. Up at the top, we have the CA code in the green, and then we have the P code in the blue below it. There's several pieces of information in here that's helpful. One of the things you might notice right away is down at the bottom you see the red square wave from 1 to 0 and 0 to 1 indicated for each 180 degree phase shift. There's this shift from the 1 to the 0 and back to 1. And this is the represented by this red square wave. Now see that the CA code is also represented by a square wave that is turned 90 degrees, or in quadrature, to the P code. This is one of the ways in which the carrier can carry both codes simultaneously on L1. Now L1 is at 1575.42 megahertz. That's its rate, which is a multiple of the fundamental clock rate, 10.23 megahertz. But again, you see the green wave going up and down, up and down, up and down on a regular basis, like a sine wave, and then it comes to the 180 degree shift, and at that moment the code chip switches. This is the way that this the square wave is perceived by the receiver. Now, of course, if there were no shift in the phase, then this would be just the pure carrier without any code. But the codes here, you see the chipping rate over on the right-hand side. Notice that the CA code chipping rate is 10 times slower than the P code. The length of a CA code is 960 feet, whereas the length of a P code, 10 times shorter, because the P code's 10 times faster, is 96 feet. And also, notice the repetition period. The CA code is repeated very quickly, whereas the P code does not repeat for 7 days, making it more secure, as would be expected with a classified precise code. Well, you see here also the 10 P codes per each CA code chip, which is exactly as you would expect. On slide 23, we just reiterate some of this information. To go over it, each shift is from 0 to 1 or 1 to 0, accompanied by a corresponding change in phase, 180 degrees. The rate are all multiples of the 10.23 megahertz fundamental clock rate. The L1 carrier is 1575.42, which is 154 times that rate, and 120 times that rate is 1227.60 megahertz. These are L1 and L2. Now, again, there will be modernized an L5 that is coming, which will be 115 times the fundamental clock rate. The chipping rate of the CA code 10 times slower than the P code. It's all known as the coarse acquisition or the civilian access code. It's in quadrature, or 90 degrees from the P code. Here on slide 24, we see the image of how the pseudo-range, the PRN code, functions, and it's some similarities to what we discussed with the EDM. You see here that in the green, the satellite signal coming down is a square wave from code states -1, +1, which correspond to the 0 and 1s of the previous slide. And in the receiver, there's a replica of a portion of that code, a portion of the CA code, just as we had with the EDM, holding a replica back home to compare to the incoming signal. But in this case, of course, the signal is coming directly down from the satellite and is received at the GPS receiver. The GPS receiver has this piece of replica code that functions something like a key in a lock. It tries to put that code and match it to correlate it with what's coming in from the satellite. Now, the way it does it is shown here in terms of multiplication. -1 times -1 is +1, and you see this little calculation, and 10 divided by 10, these 10 little multiplications divided by 10, in this particular case, at the upper tier, equals a +0.4, meaning that it is not 1. You see, when it is exactly 1, when this calculation is exactly 1, that's when there is correlation. There's a time shift here. You notice how the blue square wave can be shifted over, and there it is in the lower tier, shifted over, and matches, correlation. The calculation does result in a +1, and therefore the key fits in the lock, and the receiver knows that it is correlated to the incoming signal. The interesting thing about this is that that time shift for correlation gives the receiver the amount of time, the amount of elapsed time that it took the signal to come from the satellite to the receiver. Obviously, if the receiver knows the elapsed time, it knows the frequency of the signal, and therefore it knows the distance. Success. This is how the pseudo-random noise PRN code functions. This is the way that the distance is derived, by solving the time that it took the signal to come from the satellite to the receiver. As it says here, to conceptualize the process, one can imagine two codes generated precisely at the same time, identical in every regard, one in the satellite and one in the receiver. The satellite sends its code to the receiver, and on its arrival, the two codes don't line up. They're not correlated. The receiver then generates that replica code, and it shifts it until it fits into the received code. The time it took the signal to make the trip to the receiver is that amount of shift. And therefore, this is the solution. Now, if this was the whole story, we'd be done. And of course, it isn't the whole story. Here on slide 25, I mentioned the delay lock loop, which allows this correlation to continue. Once the GPS receiver is locked onto the signal and has its code correlated, it can remain locked as long as there isn't a cycle slip, meaning as long as there is no interruption of the signal from that satellite, it's not obstructed in any way, the receiver can continue to log the signal from the satellite and stay correlated with the delay lock loop. But one of the reasons that this isn't the whole story is something mentioned earlier, in that the clock in the satellite, the frequency standard or oscillator, and the clock in the receiver are not perfectly in sync. They cannot be. So therefore, GPS time, as we mentioned earlier, here is shown in the green, the satellite clock in the upper in blue, and the receiver clock in the lower in red. Now, the difference between the satellite clock's time and GPS time is shown in d small t. The difference in the receiver's clock from GPS time is shown in d large T. Now, the pseudo-range observable, shown here in d tau, can determine the amount of time that it took the signal to reach the receiver from the satellite. But of course, this is based upon the receiver's clock, which is by no means a very high quality clock, and the clock correction in the navigation message. Now, together, these have some difficulties. First of all, the GPS receiver clock is probably a quartz oscillator and is not terribly stable.
Also, as you know, the broadcast clock correction in the navigation message is not perfect because, of course, it was uploaded some time ago when you receive it, and so it isn't right exactly. And when we speak of time and distance, as I pointed out, a nanosecond, a billionth of a second, is approximately a foot. So therefore, the pseudo-range has some errors associated with it that are very difficult to remove. And so the pseudo-range by itself, while it has the virtue of being approximately correct, is certainly not at the level of accuracy that we have come to expect from GPS. And here on slide 27 are some of those errors. As you see from this formula, over on the left-hand side, the pseudo-range measurement equals rho, the true range, plus all of these other factors. Now, if it were correct that the pseudo-range was good and complete by itself, there wouldn't be these other factors. It would simply be the pseudo-range P equals rho, the true range. But in fact, there are, of course, satellite orbital errors because the orbits of the satellites are affected by many factors, including the variations in gravity, drag, and etc., and tidal forces from the sun, the moon, the etc., and so on. Then C, the speed of light, of course, is constant, but it has to be multiplied times the satellite clock offset from GPS time minus the receiver clock offset from GPS time. Now, while the satellite clock offset from GPS time is somewhat known from the navigation message, it's not perfectly known, and the receiver clock offset from GPS time is not well known at all. Then there's, of course, the ionospheric delay, which we've talked about a little bit. There's also a bit of tropospheric delay, a little bit different kind of delay. Then on top of that, there's something known as multipath. This means that the signal from the GPS satellite bounces off of something before it gets into the receiver. And obviously, if you're measuring distances to determine your position, that bounce creates a difficulty. And then there's receiver noise. This is like the static that can appear on your car radio. So these are all of the effects that contaminate, if you will, the pseudo-range position. So while the pseudo-range is a good way to get started with a GPS position, it isn't the full answer. Now you might ask at this point, well, if it isn't the full answer, then how do we get the extraordinary accuracies that we depend upon GPS to produce? Well, here's a convenient approximation, a rule of thumb, 1% rule of thumb. You see, generally speaking, if you're trying to use a signal to do positioning or to measure a distance, at best, everything being in your favor, you can resolve that signal to 1% of its wavelength or 1% of its chipping length. Now, you may remember that if we talk about the P code, that would mean a maximum precision of about 1% of a tenth of a microsecond or a nanosecond. 1 nanosecond multiplied times the speed of light, as I've mentioned, is about 30 centimeters and approaching a foot. And this is in direct correlation with that 96-foot chip length that we saw with the P code. 1% of that, approximately a foot. Now, CA code is 10 times less precise, so it's 10 times slower. So instead of 30 centimeters, it's maximum resolution of about 3 meters, which is, again, in direct correlation with that chipping length of 960 feet. Therefore, 1% being 9.6 feet approximately. And those are the best answers that we could get if the pseudo-range was the entire answer. But, of course, we do much better than that. And here's how we do better. That same 1% rule of thumb can illustrate how the carrier phase observable, that second observable, comes to our rescue, so to speak. With this little formula here, the length of a complete wavelength in meters is equal to the speed of light corrected for atmospheric effects divided by the frequency in hertz. Now remember that L1 is 1575.42 megahertz. So here we have a little calculation. The length of a wavelength of the L1 carrier speed of light on top here divided by 1575.42 times 10 to the 6 hertz. That shows that a wavelength in L1 is approximately 19 centimeters. Now in L2, same calculation. Here we have it, the speed of light divided by 1227.60 times 10 to the 6. That's the frequency of L2. And the calculation shows that the wavelength in L2 is approximately 24 centimeters. Therefore, the resolution available from the carrier wave observable, this is as distinct from the coded pseudo-range code phase, 1% of the wavelength on the carrier is approximately 2 millimeters. Now obviously a 3-meter ranging precision isn't adequate for most, if not many, if not most, of the GPS applications we use. However, the capability to get a position within 2 millimeters, that is the promise of GPS. And that is, of course, why we're having this discussion, because GPS does indeed have the capability of reaching those levels of accuracy. Well, that's the end of Lesson 1, and on Lesson 2 we will go further into the discussion of biases and errors.